All right, let's go.
Number 10. The problem itself. A coin toss that happened once and could never happen again. If gravity and electromagnetism were balanced even slightly differently in the first fraction of a second after the Big Bang, the universe you're sitting in right now would never have existed. Not a different universe. No universe. No stars. No atoms heavier than hydrogen. No you. Physicist Paul Davies calculated the odds of gravity and electromagnetism balancing correctly by pure chance at roughly 1 in 10 to the 40th power. To put that number into something a human brain can hold, it is the rough equivalent of aiming a single shot from Earth and hitting a coin sitting at the far edge of the observable universe, 46 billion light-years away, and hitting it perfectly on the very first try. There was no second attempt. This calibration happened once in the first trillionth of a billionth of a second of cosmic history, and it landed exactly where it needed to for atoms, stars, and chemistry to ever be possible. This is not an isolated case. Physicists have identified dozens of fundamental constants, numbers built into the laws of physics that are not derived from any deeper principle, just measured and plugged in, and an enormous number of them sit inside narrow ranges that allow a complex, life-permitting universe to exist at all. Shift several of them by single-digit percentages, and the universe collapses, disperses, or never produces a single atom heavier than hydrogen. This is the fine-tuning problem, and it has produced one of the most contested debates in modern physics. Here is every serious theory attempting to explain it. Number 9. The strong nuclear force. The margin is single digits. The strong nuclear force holds the nucleus of every atom together, overpowering the electromagnetic repulsion between positively charged protons that would otherwise tear every nucleus in the universe apart instantly. Physicists have calculated that if the strong force were weaker by more than roughly 2 to 10%, depending on the specific model used, deuterium, a critical intermediate step in stellar fusion, would become unstable, and the chain of nuclear reactions that builds heavier elements inside stars would never get started. The universe would remain almost entirely hydrogen forever. No carbon, no oxygen, no biochemistry of any kind. If the strong force were instead stronger by a comparable margin, diprotons, two protons bound together without the intervening neutron found in deuterium, would become stable. This sounds like a minor technical detail. It would catastrophically accelerate stellar fusion, causing stars to burn through their hydrogen fuel in a tiny fraction of the timescale, collapsing the multi-billion-year stable burning phase that current stars rely on into something measured in a fraction of that timescale. Far too short for any planet to develop complex life. A margin of single-digit percentage points in either direction separates a universe rich with carbon-based chemistry from one that produces almost nothing beyond hydrogen and helium. Number 8. The cosmological constant. Off by 120 orders of magnitude, and yet just right. This is widely considered the single worst prediction in the history of theoretical physics, and simultaneously one of the strongest pieces of evidence for fine-tuning anywhere in cosmology. The cosmological constant governs the rate at which the vacuum of empty space itself drives cosmic expansion, what we now call dark energy. When physicists calculate the expected value of this constant using standard quantum field theory, treating it as the vacuum energy contributed by every quantum field in existence, the predicted number comes out roughly 10 to the 120th times larger than the actual measured value in the real universe. That is not a rounding error. That is a discrepancy so large it has no comparison in ordinary experience. It would be like predicting the weight of a single atom and being off by more than the mass of the entire observable universe. And yet, the actual measured value is not zero and not enormous. It is a small, specific, positive number, just large enough to drive the accelerating expansion we observe today, and just small enough that it did not rip galaxies and stars apart before they had any chance to form. If the cosmological constant had been even modestly larger, space would have expanded so violently in the first instance after the Big Bang that matter could never have clumped together into stars or galaxies at all. The fact that it sits in this narrow, life-permitting window, despite being staggeringly far from its naively predicted value, is considered by physicist Sean Carroll and others to be among the strongest specific pieces of evidence motivating the multiverse theories discussed next. Number 7. The gravitational force constant, the weakest force doing the heaviest lifting. Gravity is, by an enormous margin, the weakest of the 4 fundamental forces. The strong nuclear force is approximately 10 to the 40th power times stronger than gravity, a ratio so large that physicists frequently illustrate it using a ruler stretched across the entire width of the observable universe to represent the scale of difference. And yet, gravity is the force responsible for holding planets in orbit, compressing the cores of stars to the point of nuclear ignition, and assembling galaxies out of primordial gas. If gravity were modestly weaker relative to the other 3 forces, matter in the early universe would never clump densely enough for stars to ignite at all. The universe would remain a thin, cold, diffuse cloud of gas indefinitely. If gravity were modestly stronger, stars would compress to ignition far too quickly and burn through their nuclear fuel in a small fraction of the time current stars take, again leaving no stable multi-billion-year window for planets to form and for life, if it could even begin, to develop in any meaningful timescale. The relative weakness of gravity compared to the other 3 forces is not derived from any deeper theory. It is simply measured. Why it sits at the specific ratio it does, roughly 10 to the 40th power weaker than the strong force, rather than some other ratio entirely, remains, like the cosmological constant, an unexplained input rather than a calculated output of current physics. Number 6. The design hypothesis. Someone or something set the dials. The most direct explanation for fine-tuning is also the most philosophically contested. The design hypothesis proposes that the precise calibration of physical constants is not coincidental, that some intentional process, agent, or principle selected or fixed these specific values rather than the universe randomly landing on a life-permitting configuration purely on chance by any additional explanatory mechanism. This argument draws directly on probability. Proponents point out that the combined improbability of dozens of independent constants, each falling within their respective narrow life-permitting ranges simultaneously, compounds into odds so vanishingly small that attributing the result to blind chance without any additional explanatory mechanism strikes many physicists and philosophers as an inadequate account on its own. The design hypothesis is typically presented as one of only a small number of logically available categories of explanation, alongside chance and necessity, for why the constants take the specific values they do. This theory sits outside mainstream physics in the sense that it is not experimentally testable using current methods. There is no proposed measurement that could confirm or falsify an intentional designer behind the constants. It remains, however, a serious position taken by a number of physicists and philosophers, distinct from and frequently contrasted against the multiversal explanations that follow. Number 5. The Anthropic Principle. We could not be asking this question in a universe that did not allow us to exist. The Anthropic Principle reframes the entire question rather than answering it directly. It states in its most basic form that any universe capable of being observed by intelligent life must necessarily have constants compatible with the existence of that life. This sounds at first almost like a logical tautology, and in its weakest form, philosophers acknowledge that it largely is. But the Anthropic Principle becomes scientifically substantive when paired with the existence of a much larger ensemble of possibilities, specifically a multiverse containing many regions or separate universes with differing physical constants. Under that combined framework, it is not surprising that we observe a finely tuned universe, because finely tuned universes are, by definition, the only ones capable of producing observers who could ask the question in the first place. Out of an enormous or infinite number of universes with randomly assigned constants, only the rare subset compatible with complexity and life would ever contain anyone wondering why their universe seems so improbably well suited to their own existence. Critics, including physicists skeptical of the framework, argue that the Anthropic Principle alone explains nothing about why a multiverse exists in the first place, and that without independent evidence for a genuine ensemble of other universes, the reasoning risks becoming circular, using our own existence to explain our own existence. The strength of the Anthropic Principle, as an explanation, is therefore tied directly to whether the underlying multiverse theories that follow turn out to be physically real. Number 4. The string theory landscape. 10 to the 500th power possible universes. String theory, in its most developed form, does not predict a single set of physical constants for the universe. It predicts an enormous number of mathematically consistent solutions, commonly estimated at upward of 10 to the 500th power distinct configurations, known collectively as the string theory landscape. Each distinct solution within this landscape corresponds to a different way the theory's extraspatial dimensions could be compactified, and each produces in principle a different effective set of physical constants when viewed from within that universe's own 4 observable dimensions. This landscape provided crucial theoretical backing for the multiverse explanation of fine-tuning because it offered a specific physical mechanism rather than mere philosophical speculation by which an enormous number of regions with genuinely different physical constants could exist. Physicist Steven Weinberg used reasoning grounded in this landscape prior to the cosmological constant's value being precisely measured to successfully predict that it should be small but non-zero, a prediction later confirmed by observation and considered by cosmologist Sean Carroll, among others, to be one of the most significant pieces of evidence currently supporting multiverse-based explanations for fine-tuning. The landscape remains entirely unconfirmed by direct experiment. String theory itself has produced no testable prediction that distinguishes it from competing frameworks, and critics note that a theory capable of producing 10 to the 500th power different possible outcomes risks being so flexible that it struggles to be falsified by any observation at all. Number 3. Eternal inflation. A universe that never stops producing new universes. Eternal inflation, first proposed in the 1980s by physicist André Linde, building on Alan Guth's original inflationary model, proposes that the same rapid exponential expansion that smoothed and flattened our observable universe in its first fraction of a second never actually stops everywhere. In most versions of the theory, inflation continues indefinitely in some regions, perpetually spawning new bubble universes, each one breaking off with its own independent Big Bang and critically its own independently determined set of physical constants, determined by which specific region of the string landscape that particular bubble happened to settle into as it formed. Combined directly with the string theory's landscape, eternal inflation provides the physical mechanism that turns the landscape's enormous number of mathematical possibilities into an enormous number of actually existing physical universes, populating the landscape rather than leaving it as pure unrealized mathematics. This combination, eternal inflation-generating bubble universes, each one landing on a different point within the string landscape's possibility space, is currently the leading physical framework underlying serious multiverse-based explanations for cosmological fine-tuning. As with string theory itself, eternal inflation has not been directly confirmed. Some indirect observational signatures have been proposed and searched for in the cosmic microwave background, including potential evidence of bubble collisions between separate inflating regions, but as of 2026, no confirmed detection of any kind has been made. Number 2. The varying constants hypothesis. What if the numbers are not even fixed? Most fine-tuning arguments assume the constants of physics are genuinely constant, fixed once, unchanging across the entire history and breadth of the universe. A minority but persistent line of research questions that assumption directly. In a series of studies, including a notable 2020 paper published in Science Advances led by physicist John Webb at NSW Sydney, researchers measured light from distant quasars, some over 13 billion light-years away, and found tiny but measurable apparent variations in the fine structure constant, the number governing the strength of the electromagnetic force, when compared across different regions of the observable universe. If confirmed and replicated, this would substantially reframe the entire fine-tuning debate. Rather than asking why our specific region of the universe, the one we happen to inhabit, landed in a life-permitting range, while the constants might differ, perhaps significantly, in regions of space far beyond what we can currently observe. These findings remain contested, have not been universally replicated by independent research groups, and are treated with appropriate caution by the wider physics community as of 2026, but they represent a genuinely active and unresolved area of observational cosmology. Number 1. The self-explaining or necessity hypothesis. What if there was only ever one option? The final major category of explanation proposes something distinct from chance, design, or a vast ensemble of alternatives. The necessity hypothesis suggests that the constants of nature might not actually be free parameters at all, that a sufficiently complete future theory of everything could show that the values we observe are not one option among many, but the only mathematically and physically consistent values that could ever have existed, derivable from first principles with no freedom to vary. Some physicists have speculated that approaches unifying gravity with the other forces at a deeper level, potentially including some quantum gravity frameworks, might eventually reveal that what currently appears to be an arbitrary, fine-tuned coincidence is, at a deeper mathematical level, simply the unique, self-consistent solution, with no other possibility ever having been available. Early hopes within parts of the string theory community, prior to the discovery of the landscape's vast number of solutions, were specifically that M-theory might eventually predict all fundamental constants uniquely, eliminating the fine-tuning problem entirely, rather than explaining it through chance or selection. This remains the most speculative and least developed explanation on this list. No current theory of everything exists in a complete experimentally confirmed form. Whether the constants are truly necessary in this deep mathematical sense, or whether they are genuinely contingent facts requiring a chance-based, designed, or selection-based explanation, remains, as of 2026, entirely unresolved. 10 theories. A coincidence so improbable it has been compared to hitting a coin at the edge of the observable universe on the very first try. A strong nuclear force balanced within single-digit percentage points. A cosmological constant off by 120 orders of magnitude in naive prediction, yet landing exactly where life requires. A design hypothesis proposing intention behind the numbers. An Anthropic Principle proposing we could only ever ask this question from inside a universe built to allow it. A string landscape of 10 to the 500th power possibilities. An eternal inflation that may be generating new universes endlessly, each with its own roll of the dice. A hint that the constants might not even be fixed at all. And a final possibility that there was never any choice to begin with, that the numbers could not have been anything other than exactly what they are. Nobody knows which of these is correct. Some may not be mutually exclusive. The universe runs on numbers nobody has ever derived from anything deeper. Numbers that, as far as current physics can tell, simply are. Subscribe to Cosmic Hives. See you in the next one.